Hello, my name is Sinwoo Kim, and this is my report for Lab 3. This report will consist of an introduction, the fundamental principles, the experiment, results and discussion, and a conclusion. For this lab, we will be using a virtual simulation lab to construct different circuits. The purpose is to predict the behaviors of circuits that contain resistors in series and in parallel, using ammeters and voltmeters to measure currents and potential differences. For the results, we got that the node and loop rules hold true, and the measured RC constant was 5.98. Here are some key principles of circuits that we'll be looking at today. The node rule, also known as Kirchhoff's current law, states that the total current entering a node is equal to the total current exiting the node. The loop rule, also known as Kirchhoff's voltage law, states that the sum of all voltage drops around any closed loop is equal to 0. And lastly, Ohm's law states that the current through a conductor between 2 points is directly proportional to the voltage across the 2 points. For the first part of the experiment, we will be looking at in-series circuits. The system is the circuit and the multimeters, and the surroundings are Earth and everything else. The first step was to predict the currents I1 and I2 that would be measured by the two ammeters, and I used Ohm's law to the right and found that the current was 0.02 amps. Since the circuit is in series, the current is the same everywhere. Now I have created that exact circuit in the simulation lab, and you can see that the ammeter measures that the current is 0.02 amps like we predicted. Reverse the connections to one of the ammeters. What does the ammeter read when inserted backwards? So I reversed the top ammeter, and you can see that the current still reads as 0.02 amps. Next, replace one of the ammeters with a voltmeter. The voltmeter has very high resistance, so the current does not flow through to the ammeter. Therefore, it reads 0 amps. The voltmeter measures a voltage drop of 3 volts, since it is the only voltage drop now. Measure the potential difference for each part of the path. I used a voltmeter from points A to B, C to D, and so on. The differences are shown, and adding them all together adds up to 0 volts total, as expected per the loop rule. Here's a graph I drew to show the potential difference along the path of the circuit. When you attach a voltmeter, you alter the circuit. Why doesn't the ammeter reading change? This is because the voltmeter has high resistance, so barely any current flows through it, and instead the current continues as before. Now replace the voltmeter with an ammeter in parallel with the 100 ohm resistor. What happens? The ammeter has much less resistance than the resistor, so the current will flow through it instead. The only resistance now is 47 ohms, so the current measured by the ammeter is higher. Here we are measuring the resistance across each part of the path, and I've used Ohm's law to do this to the right. As you can see, the calculated resistance for each of the resistors is very close to the expected values. For the second part of our experiment, we will be looking at resistor-capacitor circuits. Here we are looking at the charging and discharging of the capacitor and measuring how long it takes with a 10 ohm light bulb and a 20 ohm light bulb in the circuit. For charging, it took 7.45 seconds with a 10 ohm and 13.44 seconds with a 20 ohm. For discharging, it took 7.37 seconds for a 10 ohm and 14.33 seconds with a 20 ohm. What is the RC value, or time constant, of a circuit with a 9-volt battery, 200 millifarad capacitor, and a 30 ohm light bulb? To do this, I have measured the voltage across the capacitor while discharging at various time points. I then linearized the voltage over the original 9-volt voltage and plotted it against time. The predicted RC is 6, and the measured RC using the slope of our plotted line is 5.98. All of our results have been very close to our expected values, but not exact. Therefore, we must cover the possible sources of error, which are human error in starting and stopping a stopwatch, and the fact that online simulations are ideal and may vary from real-life experiments. To conclude this experiment, we will now cover some discussion questions. What if we did this with an actual ammeter in real life? What's the difference, and how would it have affected the circuits? The ammeters in our simulation are ideal and carry 0 resistance. However, an actual ammeter would have a low but non-zero resistance. The measured currents in real life would be slightly less than the current would be without the ammeter present. What if we did this experiment in real life, charging a capacitor with no resistor in the circuit? How quickly would our model predict the capacitor to reach full charge, and would this happen in real life? In our ideal model, the capacitor would be done charging almost instantly. In real life, the speed would be slightly more limited because there may be some resistance present in the battery or in the wiring.